Alright, so next we have to find dy dx when x squared times y cubed plus sine xy is equal to cos y plus x. Alright, so with implicit differentiation, we just apply the differential operator to both sides of the equation immediately. We have that there, and we differentiate. Alright, so let us see how we differentiate this thing here. So now we have two functions of x multiplying each other, so this is definitely product rule. So we write back one element of the function of the product, x squared. We differentiate y cubed, we get 3y squared times dy dx. Since y is a function of x, and we know if we have a function of x to a power, if you have to differentiate that, it is the power times a function of x to the power minus 1 to the n minus 1 power multiplied by ddx of that function of x. That's why this is the answer. Plus, we now write back y cubed multiplied by the derivative of x squared, which is 2x. As simple as that. Plus, differentiate sine xy, it is cos xy multiplied by the derivative of xy, which is a product rule. So we write x, differentiate y, plus we write y, and we differentiate x, we get 1. So this you're seeing here is y times 1. Alright, this is equal to, now I write this part, so this whole one line equation, this is equal to that. So if I differentiate cos of y, I will get negative sine y multiplied by the derivative of y. If I differentiate y, I just get dy dx, plus I differentiate x, I just get 1. If you differentiate just the y, you always just put ddx of y. It's nothing more complicated than that. Alright, now I'm actually finished differentiating. It's as simple as that. That's why it's in the C region. After this, we just want to multiply throughout and then group like terms. So just look carefully. What did I do here? All I did was multiply the cos xy, multiply cos xy by this term and also by that term, and that's what's here and here. I made some other things look a little more presentable. You won't put a 2 in the middle here, you put a 2 at the end. So I guess I should have put this 3 at the extreme end here, but not very it's not vital, it just makes it look a little better. Alright, so moving on quickly, I transposed all the dy dx terms on the left hand side of the equation, being careful to change signs. As few people that I have marked so far, they forgot to change some of these signs when they were transposing. Alright, anyway, so you can take your time and look through the video and you will see what we did. When we put the dy dx terms on one side of the equation, next thing to do is to just factor out the dy dx and then throw everything under here, thus making dy dx the subject of the formula, and we are finished. As simple as that. Alright, number 9. Alright, so we have something to differentiate here. Some people tried to do log differentiation on this. I don't know what you are thinking. The rule said, the very first thing on the paper said, after answer all questions, do not use log differentiation unless specifically instructed to do so. So if you did this with log differentiation, you get no marks. Alright, so we have ln x squared. At the bottom is v squared, and you write back this term here and differentiate this term. So the derivative of this term, of course, this is a product rule. So I would write back one term and differentiate the other, plus now write back the term I differentiated first and then differentiate the term I didn't differentiate first. That's what you see in there. Minus, I write the denominator, sorry, the numerator, and then differentiate the denominator, and I have that. And it's as simple as that. I made it kind of easy, not like the negative theta sine theta stuff. And you have this, just a simple simplification, and that's about it. All right, we are now on to the B region. So for the B region, we have to differentiate parametric equations. So we have those parametric equations, and we're asked to find dy dx. Now dy dx is equal to dy d phi divided by dx d phi. So if we differentiate x with respect to phi, if we differentiate y is on top, if we differentiate 3 sine phi, of course it is 3 cos phi. Alright, so if we want to find dy d phi divided by dx d phi, so if we differentiate 3 sine phi, we get 3 cos phi, minus, we want to find the derivative of this, that'll be 3 sine phi to the second power multiplied by cos phi. A function of x to the third power is 3 times the function of x to the second power multiplied by the derivative of the function of x. That's what you're seeing there. Cos is the derivative of sine. Divided by, differentiate 3 cos phi, it is negative 3 sine phi, minus cos phi cubed. Cos phi is the function of x. So a function of x to the third power differentiated is 3 times the function of x to the second power multiplied by the derivative of that function of x. That's why we have 3 times cos phi to the second power multiplied by the derivative of cos phi, which is negative sine phi. Alright, so from there, what did I do at this stage? Oh, all I did was multiply this negative by the negative and get a positive. Alright, now this is what you need to see. The majority of time you're in an exam, you get something looking like this, some really ugly looking messy problem. There will be something to factorize and simplify. You just have to put out some common term to factorize, and you most likely will see an identity popping up. Now, this is the very first and most basic identity. That's why I put this. I felt the need, not a need. I didn't see it burdensome for you to have to use this identity, since this comes from sine square x plus cos square x is equal to 1. So we factorize a cos phi and a sine phi, and we get these two terms, and this is the same as cos square phi, and this is the same as sine square phi. I think everyone should know exactly why by now, but let me just see if I can do this quickly. If we have, alright, cos square x plus sine squared x. If cos square x plus sine square x is equal to 1, then cos square x will simply be 1 minus sine squared x, and sine squared x would simply be 1 minus cos squared x. Alright? Good. Now it doesn't matter what that variable is. It could be x, phi, theta, Doesn't matter what it is. So 1 minus sine square x is 1 minus sine square phi is cos square phi. 1 minus cos square phi is sine squared phi. So this would simply be that, and it would produce negative cot cube phi. Alright, now while working this thing out, I realized that I gave you a cot to differentiate. I did give you cot on the table, but even though I did that, I had promised you I would not go past. I would not, at least, I said I wouldn't, I said don't worry with cot right now. Just focus on the basic set. So now because I said that and cot is inadvertently in the paper, it doesn't mean that I was unfair or anything. You could have still did this question. You could have still done this question without actually knowing how to differentiate cot. Right? So let's see how we would have done that. So far what we know is that dy dx is equal to negative cot cubed phi. But the question said find dy dx and the second derivative. So if we have to now find the second derivative, of course it is the derivative of the first derivative. And so this means we have to differentiate negative cot cubed phi. Since we have to differentiate negative cot cube phi with respect to x, of course we know we can't do that. We cannot do that. So we turn this operation into this operation, which is the same thing. We will find d phi of negative cot cube phi and multiply that by d phi dx. And of course this operation is similar to that operation. We said if you have to differentiate any d dx of any other variable, you write d here and write dx way over there, and whatever is a variable, you write it there and there, a shortcut, and you will get this thing out fairly quickly. Now, to differentiate this, what we would get is d phi of negative cot cube phi would be 3 cot squared phi multiplied by negative cosec squared phi. That's for cot. So this would simplify simply as 3 cot squared phi times cosec squared phi. Now, if you don't know how to differentiate cot, which you can simply work your way around it, just remember that cot is the same thing as sine as 1 over tan. Right? So instead of differentiating cot cubed phi, we have to differentiate 1 over tan cubed phi. Differentiate 1 over tan cubed phi. So we simply have a quotient rule there, and this is how we would do it: tan cubed phi to the second power, because we square the denominator and we write the denominator back here, differentiate 1, we get 0, minus, we now put the 1 and we differentiate tan phi cubed, that becomes 3 tan squared phi multiplied by sec squared phi, and then we simplify this. From here is just some simplification, right? And so you can take your time and look and pause the video or something and look through the simplification, right? And we go straight up to there, And then finally, what we would do is, all right, next you want to differentiate the fourth derivative, which would give a second derivative. So it just so happens that the fourth derivative is cot cubed phi. So now instead of, now I have to differentiate cot cubed phi with respect to x, which we cannot do. So we do an equivalent operation. We find d phi of negative cot cubed phi multiplied by d phi dx. And that's what parametric equations is all about. If we can't do dx of something, remember we said equivalent is write d here, write dx way over there, and whatever variable is here, you write d of the variable there and d of the variable here. And this would of course be equivalent to this, since that and that virtually cancels out. Alright, so to differentiate cot cubed phi is simply negative cot cubed phi, is simply negative 3 cot squared phi multiplied by negative cosec squared phi. Now, so that would mean that is the answer, as simple as that. Many people would not know how to differentiate cot, since I kind of told you don't worry with those other differentials. We can look at that at any other time. So if you are disadvantaged like that, you could have done it the next way, a simple way, with the differentials you did know. So if we know cot is the same thing as 1 over tan. So we can call cot cubed phi 1 over tan cubed phi. And we do a quotient rule. We square the denominator. And we do our usual quotient rule stuff. And you can pause and look through at what we did here. We simplify everything. A simplification, and we get the same thing. 3 cot squared phi times cosec squared phi. And it's as simple as that. So that's how we differentiate. Note, all we did so far is differentiate negative cot cubed phi. The second derivative with respect to x is d phi of negative cot cubed phi multiplied by d phi dx. So since this just gave us that, we still need to multiply this thing by d phi dx. Alright, remember this is what we're doing. So we know that this is that here. Now we need to multiply by d phi dx, since d phi was negative 3 sine cube phi. D phi dx is 1 over negative 3 sine cube phi. So we just multiply those things and we can simplify them. The things that I'm scrolling through are things that are just simplification, which you can look at and figure out for yourself. And we have that as being the answer. Right, so that's simple enough. Alright, I believe we're on to number 11. Alright, number 11, which is the last thing for the B region. Prove from first principles that the derivative of cos x is negative sin x. So of course, I didn't write the formula, but the formula is the derivative of function of x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. Since the function of x is cos x, we have cos of x plus h minus cos x divided by h. But the limit as h goes to 0 of that. Putting in h, we will get 0 over 0, which is indeterminate form. So we will have to use a trig identity, cos a minus cos b, which is negative 2 sine a plus b over 2 times sine a minus b over 2. Alright, now I don't want to say everything that's right in front of you. Just look at it. What is a? X plus h. What is b? X. So what's a plus b? X plus h plus x divided by 2. A minus B. What is A? X plus H. What is B? X. You have X plus H minus X. A minus B over 2. This breaks down to that. X plus X is 2X, of course. X minus X is 0. So that we have that here. Alright, now, of course, if you put in H, if you put in 0 at this stage, sorry, you will still get 0 over 0. We can't factorize, but what do we see any trig limit? We see something looking like a sine x over x, a sine h over 2, but we don't have h over 2 at the bottom here. That's in this case, sorry. But what we will do is multiply top and bottom of this equation by half, or we can divide top and bottom by 2, and we will then get h over 2 at the top and the bottom. Remember, we want h over 2 at the denominator, so we want to divide the denominator by 2 to get h over 2 down there, which means we must now we must also divide the denominator by 2. Whatever we do at the denominator, we must do the same thing at the numerator. Right, so we do this, and alright, so this is how the solution would pan out. We would isolate the sine of h over 2 divided by the sine h over 2. Just express it as a separate element of this product and multiply by sine of this here. So of course sine x over x, or sine r over r, sine anything over the same thing, but this limit going to the limit as the variable here is going to 0. This would just become 1. And what would this become? If h goes to 0, we have sine x plus 0, which is just sine x. So since the entire expression was negative all the time, we simply have a negative sine x.